Good morning, students. Today we are going to discuss about attribute selection measure. This attribute selection measure specifies heuristic for selecting the splitting criterion that best separates a given data partition D of class label training pupils into individual classes. As we know that decision tree algorithm, essentially decision tree algorithm contains three input parameters. First one is D, second one is attribute lists, and then third one is attribute selection measure. As you all know that D is nothing but data partition of class labeled training tuples. Then attribute list is nothing but it contains a list of attributes. Then again attribute selection measure. As I told that attribute selection measure is a heuristic for selecting the splitting criterion that best separates a given data partition. Here a heuristic is nothing but self-discovering things. So heuristic is nothing but without human intervention it will going to identify the things. It will going to discover the new things. See, it will choose the best separates a given data partition with the help of a splitting criterion. Under this attribute selection measure, it contains three kinds of things it uses. First one is information gain, and then gain ratio, and then Gini index. These are the three important information measures under that attribute selection measures. It uses these three things: information gain, gain ratio, and then Gini index. Under this, first one is information gain. See, first information gain concentrates highest information gain. Highest information gain is nothing but think you have chosen one attribute. Whatever the attribute you have chosen, that should contain highest information. That should contain highest value. We'll understand with the help of a problem in further slides about this how information gain will be working. See here, select the attribute with the highest information gain. Let Pi be the probability that an arbitrary tuple in D belongs to class Ci estimated by Ci, D divided by D. Here expected information needed to classify a tuple in D. Formula is info of D equals to minus summation of I equals to 1 to m Pi log to Pi. Here info D is nothing but it is average amount of information needed to identify the class label of a tuple in D. It's the average amount of information needed to identify the class label tuple in a given data partition D. That is nothing but info D. Then again here M is nothing but distinct classes. Pi, as you know that Pi is nothing but a probability that an arbitrary tuple in D belongs to the class Ci. Pi, where Pi uses Ci, D divided by D. That is nothing modulus of Ci, D divided by modulus of D. See, as you know that Ci, D divided by D denote the number of tuples present in given data partition D as well as Ci, D. Then again log 2. Here why we need log 2 means a log function to the base 2 is used because the information is encoded in bits. The information, whatever the information we got, that is encoded in bits. Because of that reason we are preferring log 2 function. Then second one is information needed after using A to split D into V partitions to classify D. For example, here after using A is nothing but whatever the attribute we have used to split D into number of partitions, nothing but here V partitions to classify D. Info A of D equals to summation J equals to 1 to V modulus of Dj divided by D into info Dj. Here info A of D is nothing but the expected information required to classify a tuple from D based on partitioning of A. It's expected information required to classify a particular tuple, whatever the tuple you have considered, from database D, data partition D based on partitioning by attribute A. dj divided by d can act as a weight of the jth partition. Then information gained. If you want to gain the information, if you want to check the information, we need a formula to check that how much we gained from those expected information, then information. We need to subtract the things. Info of d minus info of d. With this we will get the information gain of whatever the attribute we have considered. This is about information gain. We'll understand with one example how information gain will be working. Here we have one table, that is class label training tuples from the all electronics customer database. Under this database we have like age, income, student, credit rating, and then class wise computer. These can act as an attribute. Under this class wise computer can act as a class labeled attribute. Each and every attribute contain their own set of value. Okay, this each and every attribute contain their own set of values. We will check how this information gain will be working with this particular table. Example: induction of a decision tree using information gain. As the table presents a training set D of class label tuples randomly selected from the all electronics customer database. In this example, each attribute is discrete valued. Discrete valued is nothing but the values are not continuous. Here, each and every attribute contains different values. That is nothing but discrete valued. Continuous valued is nothing but same values. Continuous valued attributes have been generalized. The class label attribute, as I told that a BICE computer can act as a class labeled attribute. That attribute contains two different types of values, namely yes and no. Therefore, there are two distinct classes. As I told, M is nothing but distinct classes. How many attribute we used? Each and every individual attribute can act as a individual classes. That's why we preferred M in that given formula. First formula: info of d equals to minus summation of I equal to 1 to m pi log to pi. See here, m equals to 2 because f belongs to one class, no belongs to one more class. M equals to 2. Let class C1 correspond to S, then class C2 correspond to no. There are 9 tuples of class S and 5 tuples of class no. Here, according to that class labeled BICE computer contains 14 tuples totally. Under that, 9 S's, 5 no's. Initially, according to the decision tree algorithm, initially we need to create a node. That's why here we created a node n. Node n is created for the tuples in D. For the tuples in D, because whatever the tuples we are facing under given database, first initially we are creating node n for the tuples D. To find the splitting criterion for these tuples, we must compute the information gain of each attribute. That's why initially we need to consider first equation, that is nothing but, as I told that, info of d equals to minus summation of I equal to 1 to m pi log 2 of pi. This is first formula we need to use to compute the expected information needed to classify a tuple in D. Because here info of d equals to minus 9 by 14 log 2 of 9 by 14 minus 5 by 14 log 2 of 5 by 14 will get 0.940 bits. Because as I told that, according to first expected information, according to first formula, minus 9 is nothing but, according to this class labeled attribute, we have 9 S's and then 5 no's. See, according to that pi is nothing but probability of that particular thing what we used in that given information. See here, pi equals to modulus of ci comma d divided by d. See, as you know that ci comma d divided by d is nothing but the number of tuples present under that given data partition D, and as well as ci comma d. Because according to this class label attribute, BICE computer contains 9 S's and then 5 no's. Because of that reason, Ca comma D divided by D. 9 SS minus 9 divided by 14. Because of that reason we consider 9 by 14 log to 9 by 14 minus again 5 by 14. 5 is nothing but 5 nodes present under that given class labeled attribute by its computer. 5 by 14 log 2 of 5 by 14. If you can calculate, we will get the answer 0.940. Next, we need to compute the expected information requirement for each attribute. Again, we need to check like expected information about each and every attribute here. For example, initially we will consider attribute age. That attribute age contains like youth, middle-aged, senior. These are the values belongs to age category, or like age attribute. For example, since here we will check how many youths are there, then that youth contain how many S's and then how many no's for class labeled by its computer. Here for the age category youth, there are 2 S tuples and 3 no tuples. For the category middle aged, there are 4 S tuples and 0 no tuples. For the category senior, there are 3 S tuples and 2 no tuples. According to the equation 2, info A of D equals to summation j equals to 1 to v modulus of dj divided by modulus of d into info of dj. This is second formula based on expected information based on attribute. Here, according to that formula, if I can consider this thing like age attribute, under that age attribute, first initial value is youth. Youth contains like 2 S tuples and 3 no tuples. Initially, as we know that info age of D equals to 5 by 14. How we got 5? Total, how many things are there under that youth value? There are 5 tuples, 2 S tuples, 3 no tuples. Combination of these two things have 5 tuples. That's why 5 by 14 into same thing info dj is nothing but according to that first formula minus 2 by 5. 2 is nothing but S tuples, then 3 is nothing but no tuples. Minus 2 by 5 log 2 by 5 minus 3 by 5 log 3 by 5. Then plus 4 belongs to your middle aged, 5 belongs to your senior. 4 by 14 minus 4 by 4 log 4 by 4, because here we have only S tuples, 4 S tuples, 0 no tuples. That's why we don't need to consider 0th value here. Plus 5 by 14 into minus 3 S tuples minus like you have 2 no tuples. That's why minus 3 by 5 log 3 by 5 minus 2 by 5 log 2 by 5. We'll get the 0.694 bits. Once we got these expected informations based on attribute, we need to subtract info D minus info age of D. Expected information minus information what we gained based on attribute. Gain of age equals to info D minus info age of D equals to 0.940 minus 0.694 equals to 0.246. This is about only single attribute, that is age. We got 0.246. As I told that information gain concentrates only higher valued attribute information. Whatever the attribute got highest value, that information can be considered as information gain, highest information gain, that attribute. That attribute got highest information gain. That's why here we'll check individually. We checked gain of age equals to 0.246 we got. Similarly, if you can compute like this, we'll get gain of income 0.029 bits, gain of student 0.151 bits, gain of credit rating will get 0.048 bits. Because if I can compare these values, gain of age have like highest value. That's why, because age has the highest information gain among all the attributes, it is selected as a splitting attribute. Node n is labeled with the age, because node n can act as a root node. Here age can act as a root node because the remaining attributes have lower value. I mean lesser number compared to your age attribute, because those attributes have like less number, like lower numbers. That's why this particular age contains highest information. Because of that reason, we need to consider age can act as a main node or root node. Node n is labeled with age, and branches are grown for each of the attributes value. The tuples are then partitioned according as shown in following figure 8.5. Notice that tuples falling into the partition for age equals to middle aged all belong to the same class. Because they all belong to class S, a leaf should therefore be created at the end of this branch and labeled S. The final decision tree written by the algorithm was shown earlier in figure 8.2 here. According to this figure, as I told that age can act as a root node because it contains highest value, like it contains higher information gain. That's why this particular age attribute can act as a main node. Like this is a node n, because that particular age contains, like this particular attribute have three kinds of values, that is nothing but youth and then middle age and then senior. Obviously youth contains income, student, credit rating, then class, whatever the information we have in given database, those informations are present. We are going to kept those information under this particular table based on youth and based on middle age and then based on senior. Following figure, the attribute age has highest information gain and therefore becomes the splitting attribute or the root node of the decision tree. According to that, whatever the attribute contains highest information gain, obviously that will going to split further. If see here, because split further at the root node of the decision tree, branches are grown for each outcome of age. The tuples are shown partition accordingly. This is about information gain. Thank you. Remaining things we'll discuss tomorrow.